This conference will now be recorded.
Starting the recording, I realized I didn't get that going right when Heather started talking. Apologies on that. We will have this recording available if you know of folks that weren't able to join on. I know we've got a lot of folks signed up that haven't jumped on the call yet. As Heather said, we did have a photo contest this year. It was super fun and we got some really great responses. The deadline to vote is tonight. All you need to do is go to the Yakama Basin Fish and Wildlife Recovery Board Facebook page. I will post the links that will take you directly to the albums in the chat box, but you can find those just by navigating to photo albums, and they're separated into the various topics, and then you just hit like on your favorite one. So if you can go to the next slide, Heather. So our category 1 is wildlife, and these are all of our wildlife submissions that we received. Click through, and then we've got a restoration category, some real cool photos here. Go ahead. And our last one is landscape and plants. So let me know if you have any issues finding it, and in just a second I will post that link in the chat box. And then go ahead. Last but not least, just wanted to go over some ground rules for today. You should have received these in the email that included the link for today, but just a reminder to remain muted at all times, even a couple folks that aren't muted. If you've got background noise in the background, it gets really loud. Use the chat box on the GoToMeeting control panel, which is just on the right there, the little chat icon at the top right-hand side of your screen, to make a comment or ask a question. And just to make sure that everybody knows how to do that, since we've had some folks jump on, how about everybody go to your chat box right now and just let us know where you are joining us from today. Yay, Sela, Vancouver, White Salmon, Ellensburg. Awesome. Your house, I like it.
All over the place.
All over the place. So this is great. So just use that chat box whenever you've got questions. You can type them in as the speakers are talking, but the questions will be asked by facilitators after each presentation. If we run out of time for questions after the presentation, we've tried to reserve some time at the end of the day to cover any questions we didn't get to. And last but not least, you probably won't see me again, but I'm here. And if you experience any technical issues, I'm the one to reach out to. You can use the chat box. You can send me an email, whatever works. So, all right, thanks. And am I on this slide, Heather? Sorry. Maybe I thought you were jumping in here.
No, we're just going to switch over to the next speaker, I think, from here.
Okay. All right.
Great. Well, thanks, Heather and Tricia. I would like to welcome and introduce our first two speakers. The first is Tom Elliott. Tom is a habitat biologist working for the Yakama Nation on fish habitat restoration. He grew up in Virginia, exploring hardwood forests and swamps. Moving west to the San Francisco area, he immersed himself in the native flora and abundant weeds of the coastal hills while working on endangered species habitat for a national park. He earned his master's degree at Central Washington in biology, studying the riparian cottonwood forests and trying to understand the interplay between natural and human-driven processes along the Yakama River. And along with him is Bridger Cohan. Bridger is a restoration ecologist with the Yakama Nation's wildlife program. He grew up in Portland, but quickly moved to drier territory in Montana, where he completed a bachelor's in ecology. He also earned a master's degree in biology at Western Washington, spent 2 summers treating weeds and restoring alpine meadows at Mount Rainier National Park, which eventually led Bridger towards a career using active management to restore and protect our native landscapes. So from here, Tom and Bridger, I will hand it over to you.
Thank you. Tom, are you there?
Am I here?
Yep.
I hear you.
Okay, great. I had to call in because my internet service conveniently went down about an hour ago. Okay, well, thanks everybody for being here. As introduction said, I'm Tom Elliott. I work with Yakama Nation Fisheries, and I'm going to be talking a little bit about Wapato Reach Riparian Project. We were here in 2018 and did a presentation with Kevin Featherston kind of around the beginning of that project, and this is some of our findings. And this is really a team effort. Bridger and I are going to give the presentation today. Bridger's actually going to deliver the bulk of it. And then from Natural Systems Design, a lot of hard work of gathering the data in the field and in the office is reflected in this presentation. And so that would be Kevin Featherston, Scott Katz, Tim Abbey, Megan Whiteside, and Steve Winter. If you're on the air here, thank you. And finally, as always, I'd like to thank the Yakama Tribal Council because their support enables all of this work that we at the Yakama Nation get to do. Next slide, please, Bridger. So the outline of the presentation, I'm going to touch briefly on sort of the extent and importance of the Wapato Riparian Forest, just a little bit about what it is, and then talk about the project, how it started and where it's going. And then really the meat of it is number 4 here. Bridger's going to talk about the results and the implications, what that means for the Wapato Riparian Forest. And then I'm going to come back and talk about some potential restoration actions and that we can do to address the problems we found and the conclusions. Next slide, please, Bridger. The forest in the Wapato Reach is a riparian cottonwood forest that stretches from roughly Union Gap to Mapton, about 40 to 50 river miles. So this would be south of the town of Yakama. And it's a really important place because it's a pretty wild forest, 4,500 acres of it, in the middle of hundreds of thousands of acres of irrigated agriculture. So as such, it has some really important functions. One is it sustains, as it has for time immemorial, cultural resources for the Yakama people. And it's key habitat for mammals, birds, insects, and other organisms. And it's also a huge recreational resource. Next slide. So what it looks like if you're in it is it's dominated by black cottonwood, which is Populus trichocarpa, or Populus balsamifera, subspecies trichocarpa, depending on the nomenclature you like. And this is a really large riparian tree, and it's the only native large tree in our valley lowlands along rivers and riparian systems. So it creates, in its mature forest, manifestation, it creates a really wonderfully diverse, tall canopy with lots of snags, an understory of lots of riparian shrubs. So it's a multi-layered forest, lots of vines, and provides tons of wildlife habitat, and then interacts with rivers to create lots of fish habitat. Just as an illustration, on the right here, you see on your slide all these yellow dots on a stretch of river. This is about 7 miles of river downstream of Zilla, and the yellow dots are beaver dams that we've mapped. When I was back with the wildlife program, we went out in the ground and mapped these beaver dams, and there are about 50 beaver dams in this area of river, about 7 miles, and every one of those beaver dams creates a pond, has the beavers cutting down wood around it, dropping trees, creating different forms of habitat. So the beavers contribute to this really great riparian habitat mosaic. And when you drive by this forest, you kind of recognize that it's there, but I kind of feel like it's seen but not seen. I think a lot of people know it's there. They may not really appreciate how great it is and how important it is for wildlife and cultural resources. And finally, its importance is even magnified by the fact that every fish, steelhead, salmon, lamprey in the Yakama Basin has to go through parts of the Wapato Reach to get to spawning grounds and to get back out to the Columbia River. And so it's really critical that we maintain this reach in good condition for that. Next slide. This project started 2 or 3 years ago by me and some other people connecting the dots. We knew from literature, and which I was familiar with from my thesis, that in the West, wherever you have dams and regulated rivers, riparian forests can have big. And indeed, we had a 2007 study on the Yakama River by Brodney and Rood, who are leading riparian researchers. They pointed to that exact phenomenon here. It was a broad study over the entire basin, but it highlighted potential lack of regeneration by the forest, lack of young trees being brought into the population to replace trees that were dying. So that's a problem. We also obviously know that flows have been regulated in the Yakama Basin since the early 1900s. really since 1933, strongly regulated. And then from my experience out on the river, there is obviously still large enough flood power, especially in the Wapato Reach, where large sections of it are unconfined and the river can move around. There's lots of bank erosion, lots of channel jumping. And when it does that, it drags trees into the river. Trees fall into the river. And that's a totally normal alluvial river process. But if you're not replacing those trees, it can be a problem. And then combine all that with the average span of the cottonwood is pretty young. And I started wondering about the future of the forest. I started kind of being a little concerned. Next slide. And then the question which led to this study became, what is a long-term prognosis for the health and existence of the forest? So with that, Bridger, I'll turn it over to you, and you can kind of tell them what we did and what we found.
Perfect. Thank you, Tom. So, yeah, as Tom mentioned, we have our overarching question is looking at the health and continuation of that riparian forest in the Wapato Reach. And for this project, we wanted to break that down into slightly more manageable questions. First being, are the current trends in cottonwood recruitment and mortality rates leading to a sustainable for that forest? And then secondly, in the event that they're not, what strategies are going to be effective for restoration in order to maintain that forest area and its ecological integrity? And those in turn, being pretty big questions in themselves, get broken down a little bit. So as an example, looking at the recruitment and mortality rates in the forest, we were really interested in things like, what are the exact mechanisms for recruitment and loss within this reach? Are there particular hydrogeomorphic conditions that are ideal for recruitment? And are there other conditions that are useful for sustaining the forest? And then looking at the reproductive cycle of the cottonwood, are there particular checkpoints in that cycle that are a real stress or a limiting factor in recruitment? As far as restoration strategies, there's obviously a very wide range of activities that one could do in order to restore the forest. As you'll see later, we have two general categories in mind, looking at more small-scale planting projects and then also some basin-wide management. And even within those categories, it's important to know things like, what are the best methods for planting? Is there a particular timing for planting that's important? Are there other things we can do, like weed control and irrigation on plantings that are effective in getting those to recruit to a mature stand of trees? As far as the timeline for the project, Tom's covered our first step there of recognizing that potential problem. I'm going to spend just a few slides looking at kind of the conceptual model of how the cottonwood forest on the Wapato Reach grows and maintains and regenerates. And then the meat, as he mentioned, is this detailed analysis that our friends at NSD did, and looking at several of the analyses that they performed on data from this reach in terms of where trees are recruiting, how they're recruiting, and what the overall trends are for the forest. And using that information allows us to kind of formulate some alternatives for restoration, for management, and then those are kind of lumped into a short-term strategy, which is probably going to be focused more on the ground restoration, and then a longer-term, larger-scale strategy for management changes within the basin. Here's a little bit of a conceptual model. These graphics may be familiar to some of you. We have our Yakama River here. This is just a cross-section, and you can see the summer base flow, which is roughly equivalent to the water table. Down below, there are trees along the sides. Mature trees are contributing seeds about this time of year, actually. They're just wrapping up. And then we have a much higher flow level that, at least historically, would have happened every several years. Maybe about every 5 years, you have a big flood. For cottonwood reproduction, that flood is really important because it scours the surface of the alluvial plain to a mineral substrate, and it's also moist, and moist mineral substrate. So that's where the seeds land. They germinate, they develop into seedlings, and then finally saplings. Those saplings have roots that go down to where the summer base flow is. In the Wapato Reach, these trees are basically phreatophytes, so they're tied into the groundwater table. And then they'll develop into older stands, and those older stands eventually will reach to nests, where you can see on the lower graphic here, as Tom was mentioning, erosion is still a key factor in this system, and so many of them end up falling into the river as a result of bank erosion and contributing that large woody debris that we're all so fond of. So you can see on the right, there's a picture of a newly established Looks like maybe a point bar here with a whole bunch of cottonwood seedlings, quite small, and then more of these pole-sized trees that we'll focus on later, because these are the ones that are much more likely to survive into becoming reproductively mature adult trees. Here's a little bit more about that conceptual model and the reproduction. So we have a series of stages here, and each one has a little bit of a limiting factor that I'm going to highlight. So you have your seeds are dispersed, generally via water, and they need to have the right substrate to germinate on. Once they germinate, they are going to follow the water table down, but that water table cannot recede faster than about 2.5 centimeters a day. And if it does, those roots are going to be unable to keep up, and the plants will desiccate and die. The seedlings, as they get larger and that they're following the water table, are still very vulnerable to herbivory and to trampling. And they're also vulnerable, even as they mature into smaller full-phase trees, to additional high flow events. So they need that initial flood to have a good place to germinate. But then if you have a flood of the same magnitude the next year, you're very likely to have those scoured away unless they're protected somehow. And finally, you have reproductively mature adult trees. And these have a relatively low mortality compared to smaller versions, but they can still die from extreme drought if you have a really big windstorm, and then also from that erosion. And as I mentioned, their lifespan is not particularly long compared to like a Doug fir or something like that. They generally will top out about 100, 150 years. Maybe a very old cottonwood in this reach would become 200 years old, but most of them are going to senesce and die naturally before that time. So this graphic down below just shows there's this kind of Goldilocks zone between the summer base flow and then where you have a really big peak flow. And that's where you're going to have the successful recruitment of cottonwood seedlings and hopefully of full size and larger trees eventually. This is what that conceptual model looks like laid out over the landscape. So the areas in green are areas where the forest is being either maintained just because trees aren't dying, or sometimes there'll be some clonal reproduction, which is useful, but it doesn't really expand the area that's forested. And then you also have some seeding areas on the point bar and abandoned channels, things like that. And you can see here in red, we have some areas of senescence. We have some areas under attack by beaver, which certainly happens in the reach, and then also erosion. All right, so getting to the actual project, this is the Wapato Reach. This map is a little flipped, but you can see Yakama over there on the left side, and then continuing down to Mabton, that's the Wapato Reach. We were interested in two particular focus areas because the reach as a whole is just a little large to be doing analysis on overall. So we have our upper focus area here in orange and our lower focus area in yellow. We mostly relied on two sets of data. So we have aerial imagery from 1949. That imagery is quite complete. It's kind of the best set we have from that early. And it is after the dams were implemented on the Yakama River, so it's after regulation of flows. But importantly, most of the forest that you see in those images from 49 was established before that happened. So it's a pretty good snapshot of what the natural state of the reach is. And then we also have aerial imagery from 2015, and we have LiDAR imagery from 2015, both of which we use quite a bit in the analysis. And over here on the right is just a picture of what the Wapato Reach riparian forest looks like. You have a nice even age stand of cottonwoods there in the background and some meadow areas. Really, really beautiful habitat, very productive. This is just a close-up of the upper focus area. You can see lots of old meander channels. We digitized the channels over the time period between 1949, actually 37, I think, and 2015. And those the sort of the sum area occupied by those channels became the historic channel migration zone, or HMZ, and that's going to get referenced a lot in this analysis. And here's lower focus area, same thing again. You can notice lots of old channels that the river has followed. So as an example of the type of analysis that was performed here, this is the upper and lower focus area, and we went through and digitized by hand from the aerial imagery the different forest types. So we have closed canopy riparian forest, which is kind of the climax cottonwood community, and then more open riparian forest and open woodland, which in this area is often a bit of a savanna-like environment, but you have, once the bulk of the cottonwood trees in the forest senesce and die, and then you're left with a much more open ecosystem. And finally, shrub and scrub. We also did this for 2015. I don't have those images on the presentation, but we compared the images from 2015 in these same focus areas to these, from 1929 to these in 2015. Another analysis that we performed was looking at the canopy height class and using that to deduce the minimum age of forests in the reach and creating kind of an age structure. So you can see the lower focus areas in blue, upper focus area in green. And what we are able to find data-wise is the height using LiDAR data, and then the number of acres in each focus area that was in that height range. And then using some dendrochronological data that we had from previous studies, we were able to figure out what a very conservative minimum age for those stands was. So for 5 to 25 feet, that's about 7 years. For 25 to 50 feet, that's about 14 years, and so on. And then I would say that the important one, or one of the most important ones, is this last column on the right. So the 75 to 125 foot tall cottonwoods, which are kind of the mature trees throughout the reach, the minimum age for those is about 58 years, and many of them are likely quite a bit older than that. And so if you're thinking back to what Tom was mentioning about the average lifespan of the cottonwood, these don't have a ton, they don't have multiple centuries of life expectancy left. In about 50 to 60 years, we would expect to see most of them starting to senesce. So it's a little concerning. You can see here, there's a very large age class of trees in that bracket that are between 75 and 125 feet tall. And there's also a pretty large cohort that are rather small trees, very young trees. There's fewer in the cohorts in the middle, and that's somewhat concerning. Those trends are a little bit different between the reaches, but generally hold true for both reaches, or both focus areas within the reach. So this graphic has a lot going on. I'm not going to go into it in too much detail, but you can see this is looking at the recruitment of pole-sized stands, and those are the ones that we're really interested in because they're much more likely than seedlings to actually turn into adult, reproductively mature stands. And we have it broken up both by the focus area and then also by trees that are inside and outside of that historic channel migration zone. And really the important thing here is that there's a pretty narrow band of elevations above the water surface, that water surface being the summer low flows, I should clarify, where cottonwoods are recruiting into these stands. So these are just Boston Whistler plots. So you're seeing, a reasonably large majority of these pole-sized stands recruiting into maybe a meter and a half or 2 meter band elevationally, and generally more than a meter above the summer water height. So they're not establishing at all elevations throughout the reach. They tend to be pretty picky, and that's an important trait that we'll look at a little bit more. This is another analysis. So looking even more specifically, not just relative elevation above the summer flows, but which sort of features, morphological features within the alluvial plain the trees are recruiting to. So again, those pole-sized stands, and we map these with, or NSD map these with aerial imagery and with field surveys, and then kind of categorize them into 5 types. So those would be abandoned channel, the gravel bars and islands behind log jams, the top of scroll bars, the toe of point bars, and then also in high water floods, you'll get water just sweeping over the point bar, and it leaves behind deposits on top of that, and those flood deposits were another place where cotton was established. Man-made and unknown were also categories. Unknown isn't so important, but man-made is actually pretty interesting. It's in the next slide. And those are just areas where some sort of anthropogenic disturbance has removed the cover from the top of the bar surface and provided an area for cottonwood establishment. This graphic shows where we're finding establishment for seedlings in blue, and then for pole-sized trees, those ones that we're more interested in green. You can see that, interestingly, the man-made sites are actually a super productive place for pole-sized trees to recruit, which definitely bears further investigation. And then also flood deposits on top of those point bars seem to be a really key spot for recruitment, both of seedlings and then also for pole-sized trees. Scroll bars a little bit less so. The flood deposits at the end of point bars seem to be a good place for seedlings to recruit, but don't seem to generate many pole-sized stands. And then abandoned channels and log jams just don't have a ton of anything. So each of these categories is a fairly small percentage of the surface of the alluvial plain overall. And so even though we're seeing lots of recruitment in certain areas, those flood deposits on top of point bars are maybe 1% or 2% of the overall area. They're not certainly the majority. And then also, it's worth noting that those flood deposits on top of the point bar are somewhat elevated above the water surface. And so looking back at where we are seeing establishment, that actually makes sense that these are the right relative elevation to the water surface during summer low flows, that they really generate a lot of recruitment. This is getting back more into that aerial imagery that I showed at the beginning, and just a general overview of what the loss and recruitment and maintenance of forest was in each of these focus areas between 1949 and 2015. That's broken up into areas inside that historic channel migration zone and outside of it for both reaches. Then I also have the sum here at the bottom. So as an example, in that upper focus area in 1949, there was about 2,300 acres of riparian forest. Much of that was maintained, about 1,200 acres. There was also quite a bit of loss, 1,000 acres, and some recruitment. And there was 631 acres of recruitment, so that's a lot. But importantly, it's not as much as we're losing, and that is true for all the different breakouts here. No matter if it's inside or outside of the channel migration zone, and depending on which focus area, they're all losing more forest than they are gaining. It varies depending on the exact subset. So outside of the channel migration zone in the lower focus area, we're seeing a rate of loss that's roughly equivalent to the rate of recruitment for cottonwoods. But then as a counterexample, in the upper focus area within the channel migration zone, we're seeing a rate of loss that's more than double the rate of recruitment. So that's pretty alarming. This is what that looks like graphically over the focus area. This is the upper focus area. Everything red is lost, green is recruited, and then the dark blue or purple is forest that's been maintained. Nice patchwork here. You're seeing lots of areas where there is recruitment, but even more areas where there's loss. The lower focus area I find to be somewhat more interesting, even because if you look more towards the upstream section, there's actually a good bit more recruitment than there is loss. But then in the lower area, more by the State Wildlife Refuge, you can see there's really substantial loss and very little recruitment. And overall, you see loss within this reach as well over that time frame. So doing some super simple modeling. This is not ideal modeling practice, but just taking the rate of loss and extending it linearly out to 2100, we see about 500 acres of loss for the upper focus area and about 133 for the lower focus area. And if you're looking compared to the forest now for the upper focus area, that's about a 28% loss of riparian forest. But really, that's not a great comparison to make, because the last time we had a relatively natural riparian forest in that reach was actually 1949, and compared to that, there's been a 40% loss, or will be a 40% loss by 2100. So that's pretty alarming, almost half. And then same down below, it's a little bit less dire, but you still see about 11% loss compared to current conditions, and an 18% loss compared to 1949 by the year 2100 if these current trends hold. I would argue that things are actually worse than this. And that is because two reasons. One, those trees are going to be reaching senescence, and it seems likely that not a substantial amount of trees have reached senescence so far, and many more will based on that age class structure that we're seeing in the coming century. And so mortality rates for the old trees are going to increase potentially quite a lot, and we're going to start seeing more loss. The original losses should hold about steady, and then depending on what happens with recruitment, that's going to kind of make or break things. But there's no real reason to expect that recruitment will dramatically rise without some sort of intervention. There is some clonal propagation happening, as I mentioned, but it's really not going to be effective in restoring the forest to areas that have been lost. It just maintains patches for a little while longer. The other reason why things are, I would argue, even worse than they appear is that if you break this up by forest loss within the historical channel migration zone, you see almost 100% loss, or actually 100% loss by 2100. And that area, that's where the channel has been in the last 65 years. It seems relatively likely that the channel will continue in about that same area. And if you lose all of the forest along the Yakama River channel, that's really the crucial habitat or crucial element of the forest for the salmonids and other species that use the river. There's still maybe habitat outside of that area for birds and mammals and things that nest in that habitat, but in terms of large rooted degree recruitment and shade, you're losing almost all of that. Again, this is that same graphic showing the age class, and there's just a lot of trees that are somewhat older than 58 years, potentially quite a bit older than 58 years. And as that big age class there on the right starts senescing and dying in this next century, we could see some pretty drastically increased rates of loss. So implications, as I mentioned, compared to now, we're likely to see about a 28% loss in the upper focus area, 11% loss in the lower focus area. So different rates of loss, but both substantial. Likely to increase as we see increased senescence in the forest. And then also, as you lose trees, you start opening up the forest to invasion by non-native species like crack willow, silver maple, Russian olive, things like that. And additionally, we have climate change as well. There's lots of uncertainty about the effects of that. There could be some pretty severe drought, some issues with flow timing, where you're out of sync with the cottonwood reproduction cycle, fires, pests, things like that. And then finally, again, the recruitment to loss ratio tends to be the best outside of the area where you would want it the most. So those areas along the river channel and along the old channels tend to have the most loss compared to recruitment. That's really not what we want to see. So as far as ecosystem effects, you have potential for reduced shading, increased water temperature, reduced flood attenuation, reduced large rooted debris recruitment to the channel, and maybe some altered alluvial processes due to that. And then also just diminished habitat quality as you start losing that forest, and consequently increased invasibility by non-native plants into those open spaces. So in summation, the outlook for the Wapato Reach Cottonwood Forest in 2100 is rather bleak. I will leave it there, but hopefully Tom will have some uplifting news for you as we talk about potential strategies to try to restore this forest.
Thank you, Bridger. Bridger doesn't leave much to the imagination there with that last slide. Thankfully, we're going to be here trying to do something about it. The Yakama Nation, one of the great things about working for the Yakama Nation is that, you know, the tribe's going to be here into perpetuity. And so it's going to keep on trying to protect these resources and restore them. So we're kind of breaking down our restoration goals in terms of the goals into 3 goals, and then we have approaches for restoration. So the first goal is to protect what you have in terms of forest extent and the health of the forest from current and future threats. Number 2 would be to create actually new forest. That's what's not happening. As Bridger showed, just new forest is not being created at a very fast rate. And finally, along hand in hand with that is increase the abundance of young age classes. And that sounds a little technical maybe, but it's really what we're trying to do is get young trees into the population again because nature's not doing it right now. And in terms of the approaches, we've broken it down into 2 main sort of paths. One is revegetation and silvicultural methods, meaning working with the plants, planting plants, dealing with invasive species, growing plants and non-planting methods, which I can talk about a little bit. And then the second one, which is longer term than the revegetation side, is working on a managed flow regime for riparian forest regeneration. Bridger, I'm on actions 2 paths now towards a healthier forest, a slide with a picture of the dam. So in terms of protection, the threats that I worry about there are, as Bridger said, invasive species. We still have some grazing, not nearly as much as there used to be back in the 70s and 80s, but cows will preferentially eat young cottonwood trees. They'll trample seedlings, so we have to keep an eye on that. There are a lot more fire starts down in that riparian area than probably people realize. A lot of little fires are put out, and some of them get pretty big. And if they, you know, I've noticed that if the forest is old and it burns pretty hot, those trees sometimes don't resprout. Sometimes they resprout very well. So it's kind of a crapshoot in terms of the resprouting of these black cottonwoods, and we don't want there to be, you know, too much fire down there clearing forest acres out. And finally, just straightforward forest clearing for whatever purpose. And under number 1, probably the most all-encompassing way to deal with this is to protect land. And thankfully, the Yakama Nation has protected a lot of land with its wildlife areas on the right bank, the reservation side, and the Washington State Department of Fish and Wildlife has done the same on the left side. So we still have some parcels to go after and protect those forest acres, but we've made good progress so far. Number 2, the revegetation methods. You know, kind of the thing we'll probably lean on, especially at first over the next 5 to 10 years, is just planting trees. whether we're talking about cuttings or nursery stock on floodplain surfaces where the water table is close enough to the surface. And that's something that we know how to do it. You know, it may be expensive in places, it may be hard in places because of various conditions. We may need to set up irrigation systems and fencing to protect those young plantings, but that's something that can be done without, you know, further delay. Basically, we're probably, unfortunately, because of the COVID thing, going to start not this fall, but next spring. But we're going to start doing that. And then there are more non-conventional or innovative methods that we want to try in a kind of pilot project way in an adaptive framework, such as the idea of creating a small field with a well-tilled surface, bare dirt, right downwind from a grove of cottonwood trees, so that when the seeds release, we can irrigate it, have the seeds land on damp earth, germinate, and then create a little patch of forest that way. So that's something we want to try. We want to try some stand rejuvenation approaches in old stands, such as maybe using selective cutting or fire or tilling them to induce sprouting. That's something we really want to get to. And we really want to be careful about monitoring all of this so we can track what works and what doesn't. And then for management for environmental flows, number 3, it's a really simple sentence here. We want to work with partners in the basin and get some releases from dams, the right amount of water at the right time to achieve specific functions. Next slide, please, Bridger. Oops. Okay, so I'll dig a little more into both of these. Bridger, I'm on the active channel slide. So for planting, you know, I talked about planting on the floodplain, which is great, but that's where the rubber really meets the road for riparian forest and rivers is in what's Bridger's referred to as the historic migration zone or the active channel. And the reason for that is that's where all the interaction is. That's where the river is currently moving. That's where sediment's moving around. That's where trees are being recruited in. The bank's eroding, the tree falls in, creates log jams, which has all sorts of benefits. And that's where in an unregulated river seedling recruitment would happen. So we need to be able to work in the active channel to get this forest working with the river again. And that will create all kinds of feedback mechanisms. One of the most interesting ones to me is, you know, the forest itself helps build the future floodplain by trapping sand. A lot of the soils cottonwoods are on are sandy soils, and that's because they've built that floodplain up around them by slowing the water and having the sand drop out. So we need to trigger all of these processes by planting in the active channel. And you can see here the active channel, if you're not familiar with the term, is just the area of current work where the work's being done by the river. It's within this dashed white line. You can see a lot of bare gravel, a few small patches of trees within that white line. And the forces in this area can be pretty powerful. There's a lot of deep, fast water, a lot of gravel rumbling along the bottom of that could really wipe out young plantings or seedlings. But we need to be able to work here. So in order to do that, we need to target some areas. We can't just say we're going to plant the active channel. Next slide, Bridger. You see here, I've broken it down more simply into bar surfaces at the right elevation, where I've roughly sketched out here in orange. Those are planting targets. Back channels or chute channels that kind of cut around behind a gravel bar during higher flows. Those are targets. Those are areas where we see them naturally recruiting and we'd like to plant. And then finally, side channels that might get cut off where the flow is more gentle. That's another planting target. Here we have a channel in the process of cutting off where I've labeled it side channel, and that might be a future planting site. Next slide, please. So in order to do this, we're not just going to be able to go out probably and stick a bunch of bare root seedlings grown in a nursery or cuttings or whatever, even container plots, in the ground on these gravel bars and expect them to live. We're going to have to give them safe sites. We're going to have to give them hydraulic shelter. And you can visualize this. You can visualize structures as these red stars. Might be a big artificial wood jam, might be something we've taken to call it. I think Tim Abbey thought of this, a caddis structure where you may take some cobble, roll it up in a biodegradable fabric and set it upstream of your planting zone to be a temporary shelter. But it's kind of like on a windy day, you take shelter behind a tree or a building, you find that calm air. It's exactly the same with water. When the water's flowing hard during a flood, we want there to be these still places behind these roughness factors in the channel, whatever they may be, to provide shelter for these young vulnerable plants. And we might actually be able to do this with naturally recruiting seedlings by putting shelter upstream of them just to help them successfully establish as poles. So this is sort of a concept, but it's something I have hope for. There's definitely going to be pilot projects. It's definitely going to be a learning experience. So I expect us to go through some different variations of this, but this is one thing I hope will really get us to be able to work in the active channel. And the next thing is, I'll talk about environmental flows, but I just want to say, as we plant, we're probably going to be able to or want to do this in concert with some environmental flow releases to help those newly planted plants get enough water to make sure the water table is high enough. Next slide. So when we talk about riparian flows, we're not talking about taking the river back to a pre-regulation condition. That's not realistic. That's not what we're shooting for. What we're shooting for is providing key functions. And to help understand this, there's more Wapato Reach specific conceptual model that Bridger went over. And this, what I'm showing you here, this graph with the red and the blue lines is widely referred to in the riparian literature as a recruitment box model. So it's a real rule of thumb kind of model to help understand what's needed to have natural seedling recruitment and what might be wrong with a regulated river that's not producing seedlings. So here in blue, you see the estimated unregulated flow in the Wapato Reach. And in red is the observed or the actual measured unregulated flow. So, and if you look at that black box with the solid black lines, that's the original recruitment box where everything lines up perfectly. There's a sweet spot where the seeds are dropping in June. That's something we don't control. They're going to drop in June or late May, whatever we do. The water's got to be at the right elevation during that time. And historically it was probably pretty frequently for those seeds to be deposited the right elevation band in the active channel to survive future scour and not too high so they don't dry out and die. And then the water declines nicely. They have contact with the capillary fringe of the water table and they establish frequently enough to sustain the forest. What we have here is, in this river, is you see the dashed black box. I really should call it the anti-recruitment box. It's not working. And you can see right away on the y-axis of this graph, which could equally represent water surface as well as volume, so in other words, elevation above base flow, that recruitment box is low. And if you go to the pictures I have here on the left side of your screen, you see the upper picture, another one of abundant seedling regermination, probably within 1 to 2 feet of the summer base flow, followed by the lower left, bare gravel surfaces, either caused by scour, there was a flood, and the seedlings either got scoured out, or they got about 6 inches of gravel plopped on top of them and they died. So that's our problem. We're going to have to find ways to address specific flow functions to get the seeds high enough on the active channel to survive, and then and to basically to be high enough to escape floods and not too high so they don't dry out. So that's our challenge. Next slide. So finally, I should have advanced here more quickly, but I guess just to touch on a few more aspects of riparian flows. First of all, Bridger did this nice Venn diagram on the upper right, which I liked. I changed the labels a little bit, Bridger, but we need flows to be operationally feasible, meaning the dams can actually do those releases, and that's possible in this basin. We need them to be scientifically sound, so we have some more homework to do with the data to understand exactly when the trees are in peak seed and exactly how high we need to get the water in this active channel, and how we can measure that. But we can do that. That's been done in many rivers throughout the West. We know how to do that. What's really important is the politically possible, meaning lots of conversations with partners, lots of consensus, lots of building support before we rush ahead. We need to do this right. We need to get everybody's support behind us. So we're a ways off on doing riparian flows, but the payoff is very efficient, very large-scale seedling recruitment, treating the entire reach at once instead of working on a project basis. So the payoff is worth all the work. Two more final points. The best way to do these environmental flows, in my opinion, is to do multi-objective flows or multi-species flows. So, for example, smolt migration in the Yakama Basin is in the months of May and June, and that overlaps, not coincidentally, with peak seed release from cottonwoods and willows. And so we could, in theory, do a flow that helps smolts move out of the river faster, that reduces their mortality on their way to the Columbia and thence to the ocean. And those flow releases already happen very regularly, run by the fisheries program in conjunction with partners. So, for example, this spring, there have been smolt migration releases. I can imagine in future years, once we get everything worked out, sort of jumping on those coattails and changing it just a little bit, tweaking it so we get something that works for trees as well. And then the other thing you need for that kind of thing, of course, is water. You need water that you can use for those purposes. And the Yakama Basin, all the partners working together have done a great job of steadily adding to our conservation in-stream flow bucket, water that can be used and shaped for in-stream flow, mostly by hard-working irrigation districts, to save water and enable us to use it for these environmental purposes. So there's definitely hope. I'm feeling pretty positive about it, but it's still going to take some time. Next slide, please. So conclusion, the forest is not on a good trend. It's not on a good trajectory. You know, I'm not sure we nailed the percentages in our study. It was definitely a sort of management level study, but it seems very clear which way the arrow is pointed. The arrow is pointed towards incremental forest loss over the next coming decades, resulting in a smaller, older, and less healthy forest by, say, 2100. The good news is, next slide, please. This is the last slide. There's definite things that we can do, and we're going to take action. We're going to implement these pilot projects I was talking about. We're going to do it in an adaptive framework so we know it works. We're going to continue to manage flow discussion, and we're going to do the necessary studies to build our science to have a really robust and a strong base for that managed flow when the time comes. And finally, this summer, we'll finish working on this project, which will mean we'll have a long-term stewardship plan in place so that Yakama Nation, working with partners, can have the right tools to sustain this beautiful, productive, and marvelous forest into perpetuity. Question slide, please, Bridger. And with that, I guess we have a few minutes for questions. I'm not sure how much time we have left, but if there are any quick questions, Tricia or Heather, Bridger and I will do our best to answer them.